So the ionic structures are a little bit different. The crystalline structures are related to those unit cells, but now we have two different types of ions, a cation and an anion. And here we're looking at the coordination number being the number of close cation-anion interactions. Coordination number would be the same. If the sizes of the cation and the anion are similar to each other, it's going to be more like a perfect cubic unit cell, or one of those unit cells, and you're going to have a higher coordination number. You also have to take into account charge neutrality and the different sizes, right? So if you have calcium chloride, you have one calcium ion and two chloride ions. How do we fit all those guys in the unit cell? Here's cesium chloride. This is an example of an ionic solid where the ions are similar in size. So this one makes a simple cubic cell. Now, why is that not called a body-centered cubic? This is a different element than the ones at the corners. The pictures we were looking at had a different color in here, but we said at the beginning they are all the same kind of atom. So what we're looking at here is one of the ions. Here we're doing chloride. We're looking at this structure based on how the chlorides are arranged and then where the cesiums fit in between them. So this green shows a simple cubic cell. And then we've got the one cation in there.
So how's the coordination number there 8 and not 6?
Well, because we're not counting these guys being next to each other, we're counting cesium atom being next to the chloride ion. I understand your question. We don't need to worry about that. So you'd be counting how many of these ions.
Yeah. So then, let's say if it was like a simple cubic one, when I count that, I count it touching 7. So how's it 6?
Well, so this one is touching 8.
Oh, no. So let's say we're going off the basis. Let's say it's like a simple cubic
Mm-hmm.
where it's supposed to be 6.
So
we're going off the chlorine.
So if you think about this guy, he's got one above, one to the side, one in front. There would be another to the left, and another down, and another behind. Yeah. It's a bit to get your mind around. So in sodium chloride, the sodium ions are a lot smaller than the chloride ions. And so if these were just like marbles or something, we could get a whole lot more in there than this structure. But because of charge neutrality, we have to have an equal number of sodium ions and chloride ions. And so the chloride ions here are going to occupy a face-centered cubic structure. You're like, what? Wait, what? Okay, so there's one of the faces, and there's an atom or an ion on the face, right? And up here, this guy's in the middle. So that's face-centered cubic with the chloride ions, and then the sodium ions are in between. So asking you how many of each ion, that's something that could happen. So try not to think about the whole thing. Let's just look at the cubic unit cell, right? I'm sorry, it was the face-centered. Face-centered unit cell, we've got half of an atom on each face, right? So there's 3 atoms, and all the corners together make 1. So there's 4 atoms in the unit cell. 4 of the green ones. We know from the formula that there has to be an equal number of sodium ions. So if this structure, if this cube contains 2 sodium ions, 4, good grief, I'm confusing myself. The simple is 1, and this is body-centered is 2, and this is face-centered, which is 4. So if this cell contains 4 chloride ions, it has to have 4 sodium ions. That make sense?
Why is the center one not count? Because I could see the 4 sodium ones. That's 1, 2, 3, 4. And I see 5 chlorine.
Because you have an eighth of this one, and an eighth of that one, and an eighth of this one, and an eighth of that one. So that's on all the corners. So that adds up to 1. And on the face, this guy, not the whole ion isn't in the cell, only half of it is. So half, and another 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 half.
Cube, not just the one side. You like use the one side and then multiply that by however many of each. I thought when you're counting it, you just count the one.
Well, it goes back to those other unit cells. So let's just go there real. So this is the simple cubic, the body-centered, and the face-centered. And here, the gold atoms are the same as the purple. It's not a different type of atom. So the face-centered cubic, when we look at full atoms, we are looking at the unit cell plus parts of neighboring unit cells. Okay? We really need to cut it like this. So the face-centered, where is it? Like that. So this illustration is showing the parts of those atoms that are actually within the unit cell.
Okay, but not the ones that are adjacent that you would have to count as well.
Well, you're not going to have to count anything else. So this would be the chloride ions. Okay, that would be the chloride ions. And yes, counting the other things, I don't recommend it. Look at the formula. NaCl. For every chloride ion, there's 1 sodium ion. So in that unit cell, if there's 4 chloride ions, there has to be 4 sodium ions. Whether I can see that in the picture or not. Okay. When the size is different, then things get different. So here we have the sulfide ions in the face-centered unit cell again. But now the zinc ions are in different places. They are within this tetrahedral hole, which is different than the chloride ions here. Kind of hard to see. And that's why I say it's better to look at the ratio. So if I were asked about this one, okay, it's face-centered with sulfide ions. That means there are 4 sulfide ions, right? In this structure, zinc sulfide, how many zinc ions would there have to be? There would have to be 4. Looking at this, it's kind of hard to tell, are those actually inside the cell or on the edges? That's just if you have different sizes. What if you have different charges? Well, now we have a 1-to-2 ratio. And so this one, here we're showing the calcium ions as the unit cell. So here's one face. And what's in the middle of the face? The calcium ions. So I have calcium ions at the corners, and I have a calcium ion centered on the face. This is face centered, right? So how many calcium ions are there? 4. How many fluoride ions? 8, because there's twice as many. So now these guys are filling all 8 of the tetrahedral holes. So this is a 1-to-2 cation to anion ratio. It's called the fluorite structure. Antifluorite is just basically the reverse. It's a 2-to-1. You don't need to know those guys.